Hello, I hope everyone is doing well. Today I am going to talk about the Lagrangian. And to start off, I'm going to be talking about Newtonian force F equals ma. I'm going to talk about how that relates to the Lagrangian and why the Lagrangian maybe is a bit better. And then I'm going to talk a bit about action in symmetries, which is related to the Lagrangian. Anyhow, so starting off with 1, so the Newtonian F equals ma. First, we're going to talk about just a particle in space. We're going to be saying that this has an active force of gravity acting on it, which is negative mg. If we were to act upon this or look at this in terms of the Newtonian mechanics, we would first say, okay, well, what is the sum of all of the forces? We would see that the force, at least in this case, is just mg, negative mg. And from there, we can see that a, the acceleration, is equal to negative g, right here, which means that x of double prime, this is equal to the acceleration, this is equal to negative g. From here, we can also see that the velocity, which is equal to the second derivative of x, the first derivative of the position x, we can see that this is just by integrating it, which is g dt, because we're looking at over the time right here. And then from there, we can see that this is minus gt plus a constant, which in this case is the initial velocity. And of course, we can go even one further, which is x, which is just x of t. Then in order to find this, we have to integrate the velocity, this one right here, minus gt plus v naught, all by t. And then from this, we can see once you do that integral, it's minus 1/2 gt squared plus v naught t plus x naught, because we get that constant at the end. We can see that this is just the kinematic equations as well, which is kind of cool. But this might be a simple example. However, once we go into examples of changing the coordinate system, once we have lots of things or forces, we don't want to necessarily, the consistent amount of vectors is quite annoying to deal with, which is why Lagrange thought, what if I had the mechanics or the classical mechanics formula, but just in terms of energy? So this gets into the Lagrangian, which is, Lagrangian is equal to k minus u or t minus u. Same thing, this is just kinetic. This is all the potentials. Doesn't look great. Potential. There we go. And then from here, once you have the Lagrangian, what you do is you plug it into the Euler-Lagrange equation, which is, I'll talk a little bit about what this means, but I might try to derive it in a future video. Right here, and then dq equals Lagrangian dq. And this is just, yeah, so here we don't need, we can use multiple coordinates. We don't need to deal with all the vectors. So now that we have that, let's look at some examples. What if we have kinetic energy of 1/2 mv squared, which is also equal to 1/2 mv squared, And then we have some potential, which is, we'll just say mgx. Can we get the Newtonian F equals ma equation like we did above, like for literally this example? But just assuming this example, but in terms of its energy, the energies of that system. Well, we definitely can. So we can see, just looking at the first part of this equation, we can see d dt, the Lagrangian dx prime. And we can see from that it is d dt mx, right? Because that 2 came down, now we just have mx. And then once we take the time derivative, this is a function of time, so we have mx m double prime. Now we take the next one, the Lagrangian of just dx. What is this going to be? Now we are just going to look at, oh, wait, now that I see this, I didn't even put down the Lagrangian. That is silly of me. Lagrangian is 1/2 mx squared minus mgx. So when we took the derivative right here, this one right here, because there was no x prime, x dot, this would go to 0, so we only look at this equation right here in the front, and then this one went to 0 in that case. However, in this case, this goes to 0, and then this is the one that we use. So in this case, we're looking at just of dx mg right here. So, but now let's put them together. And we can see that this is equal to minus mg, which is the minus g. So just like what we had before up here. So we can see that this is, in fact, this does work. This does work with Newtonian laws and beyond with that. And to just visualize this equation a bit, let's look at both of these right here. So, as I said before, I will go further into this another time, but to just get a bit of a better example, this right here is the energy with respect to its change of x, or velocity in this case. This is something that we can actually be related to the momentum. And one thing that we do know is that force is equal to dp over dt. And we can see right here, we do take the time of this. So this right here of ddt is in fact dp over dt, which is equal to the force. Looking at the Lagrangian for right here of the position, that is actually related to, or we know that force is equal to minus du over dx, right? So we can actually see that this right here is the energy, and this is actually over its the variable of itself. So in both these cases would be the position. So we can see that this is also equal to a force in a way. And if we take the Lagrangian equation, ddt of Lagrangian over dx prime. Now I'm just going to flip over this to the other side, so equals 0. So this right here, as you can see, I literally just put this over to the other side. I subtracted it, equals 0. We can see that if we were to plug in these, both of these in, we would get f minus f equals 0. So just to give a bit of a brief, understanding of this, but as I said before, I will probably derive it. So action symmetry. So just for to incite what this is related to. One, it's related to this thing known as S, which is the Lagrangian. basically you sum up the Lagrangian at every point along some time, and that is the action, which stems from the principle of least action. And this is that all paths a particle can partake follow one that minimizes, or I guess maximizes, this value right here, and then it will take that path. And this is actually also related to the Feynman path integrals, of which path is a key word right there. And we can see this in actually almost in many parts in nature. It's like this is a very fundamental law in mechanics. It's also related to Noether's theorem, which is something I might actually do another time. This is a very hefty math theorem, but it is something that is so important, especially within quantum mechanics, quantum field theory, where essentially it is saying that conservation laws are symmetries, and vice versa. And this is actually based on the Lagrangian. So yeah, thank you so much for listening. I hope you are all having a wonderful day, and thank you. Let me know if I made any mistakes, and I hope you learned something new about the Lagrangian.